Hello, I'm Dr. Andrew Halfpenny. I'm the Director of Technology for HBK's Encode product brand. And today I'd like to talk to you about understanding and improving the performance and durability and reliability of electric vehicles. So first of all, just an obligatory start really to the HBK's products and where they fit in with this. So as part of this presentation, you will see the eDrive system from HBK. So this is data acquisition and monitoring of electric drive systems, and we'll talk about that. There's going to be LDS shaker systems as well for qualification of battery packs. And of course, where I'm from, the Encode group, then we're going to be looking at using analytical software. So particularly data analytics, fatigue and durability, and reliability engineering. Because software is all about transforming those measurements into actionable information that we can use in design and maintenance planning. So first of all, back around about 3 years ago, this started for me when my boss said, we're getting a lot of our customers now using software for designing electric vehicles. So I want you to take them out for coffee and try and find out, what are they using the software for today? What are their primary challenges and what can we do to help them? So by fitting them into these three groups, I was able to try and capture some of the core questions that customers had. So to start with, in the mechanical and durability aspects, one of the key things was realizing that batteries are mechanical structures and that we can reduce battery degradation by designing them for fatigue. So we'll talk about that to start with. But then it's all about trying to understand those vibration loads much better in order that we can get better design. So it's understanding vibration, but also thermal loads, and also to try and get more representative vibration tests as well, because the shaker table tests that we use on batteries today weren't necessarily derived for the loads that are going into the battery and where the batteries are located on the vehicle platform. So how do we represent that better? And then finally, to try and get lighter, more compact batteries and more durable vehicles as well. So there's this big move in lightweighting of the battery structure as well as the vehicle structure as well to get the better range and efficiency out of it. So let's have a look at some of those to start with. So first of all, when we think of an electric vehicle battery, we tend to think of a big black box. But if actually we start to strip that down, we see that that battery pack is made up actually at the heart of it of thousands of little cells. Now they may be cylindrical cells like torch batteries as we see here, or they could be prismatic cells like the laminated foil pouch which is gaining in popularity, or hard cases. Now these provide voltages of between 2.8, 4.2 volts, normally about 3.7 volts each. And what we do is we connect those together both structurally and electrically in series and in parallel, so into modules. So each module now is producing, well, usually less than 60 volts, which is the safety limit for high voltage handling of DC. So these are the electrical and the mechanical combination of cells into modules. And then these modules are then wired in series in order to create the high voltage battery packs that we see here. But if we have a look at these cylindrical cells for an example, we see that we now have thousands of cells all joined together in what is a fairly flexible structure. So we've got this big mass spring damper system with a fairly flexible joint and structure bouncing up and down. So you can see where I'm coming with this. This is a very lightly damped vibrating system. And typically there may be sort of 5,000 to 6,000 of these cells in our battery. So that's going to be upwards of 10,000 joints in one battery. And each of these joints are like little welds and they're sensitive to fatigue. So what we're finding here is that batteries are mechanical structures and they're subject at their heart to vibrothermal fatigue of those joints. Now when the joint fails, it's not the death of the battery. What it leads to, though, is that cell can no longer store charge for the battery, and so it's manifesting itself as this progressive battery degradation that we're seeing here. So by understanding this and designing the fatigue better, it means we can get better batteries. But it's not a simple task. So we've got a vibrothermal fatigue problem of a joint. the battery is subjected to quite a broad frequency range, and it also has a very variable frequency response. And the damping in particular, which is the thing that absorbs the energy at resonance, that's also quite variable. So we need to understand that better and do more measurements on that. Now, in addition to that, our battery pack is also part of the vehicle structure. So that means not only is it inertially loaded by these heavy batteries bouncing up and down, but it also has the structural load. It has to transfer road loads through the chassis and offer crash protection too. So we've got this structural fatigue in there. And of course, there may not be wholly metallic components in there too. So we've got adhesive joints, hybrid joints, because we need to get the weight down. We need to make sure there's no high voltage risk with the battery pack and things like that. So again, there's lots of novel things going on that we're using in a fatigue related sense. So it's a really quite a challenging task. One of my customers put it this way. He said, electric vehicle batteries are not just electrochemical systems, they're also complex mechanical structures, and we, the automotive OEMs, are the structures experts. He also said, had we realised this at the beginning, we might not have given the job of designing our batteries to a bunch of electrochemical engineers. We're the mechanical structures experts. So it's a big realisation of that. So when we look at those joints, how do we design those for fatigue? Well, obviously, probably the nearest thing that we have that we use today is probably the spot weld. So that's very typical to these particular types of joints. And the spot welds in general, we're doing a lot more testing of those in vehicle lightweighting, joining dissimilar thicknesses and types of material together. So if we take a structural account of how do we characterize a spot weld, for instance, we usually start by these two fatigue tests. So here we've got a lap shear component, which is predominantly membrane stressors, and we've also got coach peel as well, which is a prying or bending type force. And if we test those in a test rig, what we actually get is SN curves essentially, but they're load versus life curves. And what we've got to do is turn those into a stress versus life curve. So how do we go from load to stress? So for that, we effectively treat our coupons in the lab as components. So we produce a finite element model. And it's important when we do this that we use the same mesh guidelines as is being used in the body in white model or the battery structural model to make sure that our stress recovery methods are the same as what's being used in industry. Now, these coarse meshes that we usually use, these load transfer meshes, give us a load or at the spot weld. And we run that through effectively a constitutive model to derive engineering stresses. And in order to gain the fatigue properties, we run this through quite a highly non-linear optimizer such that we can iterate on those constitutive models and the fatigue models so that they collapse onto a single curve. And that is then how we derive the properties for that spot weld type curve. And if you looked in our lab today, had COVID not been on, then you would be able to see many different tests of these sort of joints going on, and some of them may be hybrid joints too. I've had to grey them out here so that we don't reveal anything, but we can see a tensile test there. You can see a 3-point bend test, and you can see here this is a typical sort of coach peel setup. You'll also notice that every one of the tests also has cameras now, and that's because with these joints it's important that we can go back and see where did the failure start and how did it develop. Was it in the nugget, was it in the sheet, and things like that, rather than really doing a post-mortem on it afterwards. The cameras help us to get there. So the cameras are invaluable, really. Now that's how we could do it for a structural spot weld, and we do that in the vehicle lightweighting right now. But how are we going to characterise the joints, say, in a battery? So we've been doing work with the University of Sheffield to try and get a much more efficient process for this. And this started by having the ability to automatically detect weld failures. So the setup that they used at Sheffield was to have an electrodynamic shaker with a stinger, and that was to shake the battery module. and then we can use a laser interferometer to start to look for the vibrations. And actually what we find is we can detect the failed cells very easily. So as the joint fails, even before it's lost electrical contact, we start to see this emerging natural frequency really coming out predominantly on here. So we've now got an automatic way to detect failures through the fatigue test. So the plan that we're looking to do now is to actually produce a module on the shaker table and start to excite that. And then simultaneously, we're going to use a scanning laser vibrometer to scan that and look for where we've got failures. Now, we're not going to stop the test when the first weld fails. What the idea is that we're going to carry on testing, and we're also going to do progressive remodeling, remeshing of our FE model too, to take account. Because one thing we've found from the work with Sheffield is when we start to get a failure, then there is a local reduction in stiffness and there's therefore a preferential failure site next to it. And we need to be able to model that too. So the approach here is with one module, we should get probably around about 15 points on that SN curve. Now, we also need to test it and excite it at different RMS levels as well, because by doing that, that means we can actually pass it through our vibrothermal fatigue analysis to do the optimization. And so now we can start to collapse and derive an SN curve based on vibrothermal fatigue. So this is the approach that we're looking at to try and identify and classify those joints and connections to make sure that we can design more durable batteries. Now, one thing is, knowing the battery curve, if you like, the battery SN curve is one thing, but we also need to know much better what the real loads are going into these batteries too. So we're going to go back really to the tried and tested approach. So a friend of mine at General Motors once said to me, he said, there are three groups of people who are interested in fatigue. There's the simulation engineers who try to break things, who design things, not to break. There's the qualification engineers who try to break things. And then there's the customers who have an uncanny ability of succeeding. So the idea is that we start with the customers to characterize what the customers are doing with vehicles. We build qualification tests that are statistically representative of that, and then we simulate the tests. And the nice thing about this is if there's a failure detected at any point in that, we can actually use simulation to help us to avoid it and to get design over it. So where do we start? Well, we do have legacy data. You know, a lot of the electric vehicles are not unlike the use cases that we get on vehicles today. So there are some differences, but a lot of it on the road is very similar. But it is important that we recharacterize some of these because the batteries are positioned in a different position in the platform and therefore are more sensitive to some loads than others. We may not have gone into detail because we've never had very expensive components in this place before, so we may not have a good understanding. It may be a bit too conservative in some cases or miss bits. So there is still a need to go out and measure the real loads on the vehicles. Now, the idea is that we take our statistical customer and then we make that scientifically reproducible on a proving ground. We can't go out and do massive customer exercises every design iteration. We want to bring that in and make it scientifically reproducible. Then we take those proving ground tests and bring them into the laboratory, and we create accelerated laboratory tests. And these are on a component level, so they're much more efficient in that way. And then, of course, our goal is to simulate the qualification test. In this way, if anything fails at any point in here, we can go back and we can start to sort out what we need to do to fix the design. So what do we do then when it comes to the battery? Well, again, a good way of doing this is accelerated vibration testing. So originally this was derived for the military and we've used it an awful lot in helicopters. However, it's been really useful in ground vehicles as well, and it applies perfectly to batteries. So on the proving ground, we can now measure the vibration going into the battery. And we characterize that using two spectra, the shock response spectra and the fatigue damage spectra. Now, if you're new to this, There are many papers I can point you to, but if you think normally we represent vibrations of PSD, a power spectral density, and on that one we've got a y-axis of mean squared amplitude and an x-axis of frequency. With our shock response, our y-axis now is the worst shock, and in our fatigue damage response, our y-axis is fatigue, and in both of them the x-axis is frequency. So as we're driving our car over the road, as we hit potholes, then if the pothole was worse than it was seen before, then you'll see that the shock response jumps up. So this is representing the worst response we've seen, whereas the fatigue damage spectrum is representing the cumulative effect of vibration and shock. So this rises throughout the test. So now we can use Miner's rule and we can add the damages together to create our usage scenario. And this means that we can now create shaker table tests which are far more representative and statistically controllable as well. So in this case, we can make sure our test has at least the same fatigue damage spectra with a known amount of exaggeration or reliability and confidence. And we can also make sure that when we accelerate our tests, that we don't accelerate it too much, that we end up exceeding the worst load it will see in practice, because that could change the load path by introducing local plasticities. So this approach then helps us to develop much more characteristic tests to get a better understanding of how batteries are used so we can design better batteries. So in this then, just to conclude this part, what did we look at? Well, we found out from the interviews that batteries are mechanical structures, and we can reduce battery degradation if we can understand them and design them for fatigue. So our battery, we understand, is a vibrothermal fatigue problem. There's resonance issues and variable damping control. There's thousands of fatigue sensitive joints that we can work on. So understanding damping, understanding the frequency response function, and then designing better quality and more durable joining solutions. But in addition to that, the battery is also part of the vehicle structure. So we also have these structural loads going through it. So this is what we're working on now with the fatigue of batteries. We also saw that we need to understand that vibration and thermal loads much more, and we need to build more representative tests. So these now have a large frequency range. It's not just ground vibration, but you'll also get things like the electrical drive effects at much higher frequencies coming into that, like torque ripple and things like that too. There's complex internal structure that we need to look at, and there's this progressive failure, this performance degradation we need to look at. And finally, let's not forget, we want to have lighter, more durable batteries and a lighter, more durable vehicle structure too. So lots of work going on in our labs right now at jointing of dissimilar materials. So looking at welds, rivets, self-piercing rivets, adhesives, hybrid joints and so on. But you'll also find two rigs are running with additively manufactured components, so 3D printing of metals. You'll also see fatigue of composites, and we're also started working with Warwick Manufacturing Group and several others looking at circular economy effects as well. So these are things like trying to work out structural aging through the life of a vehicle to reuse whole components rather than melting down all the metals again. So again, lots of work going on to make these more environmentally friendly. So that's a really quick run through mechanical and durability. Let's have another equally quick run through performance and efficiency aspects. So here, our interviews with the customers were saying, you know, we want a better vehicle range and we need a better energy density as well. Lithium ion will not come close to diesel and gasoline and petroleum. So we need to get that energy density better. And this is all about maximising efficiency and minimising loss. We also need to be far more accurate in our calculations and measurements. And we need a better thermal performance, because that we know is critical to the longevity of the battery. And also, we need a much better understanding of real customer usage through the world. So how do we do that then? So first of all, an electric vehicle transfers energy from one form into another and back again. And with each transfer of energy, then we get an efficiency loss. And if we can measure that and understand it, it means we've got a good chance of minimizing it. So our journey starts, for me, with the eDrive system, which it's a wonderful piece of kit. It's a really high-speed data acquisition system, really, and it can measure the electrical and the mechanical loads at terrific speed, and therefore they're in phase with each other. And that means we can start to look at the efficiency losses between these energy transformations. As an example here, we can actually look at the AC power, for instance, and see the current, the voltage, and we can compute things like the instantaneous power. And the eDrive has its own onboard computing facilities too. So it can produce the maps of active, reactive and apparent power that we'll talk about in a minute. And it can do that to the half cycle, so the half fundamental resolution. But of course, by having the ability to store high frequency data, we can also do post-processing. And this post-processing doesn't have the burden of having to be real time, so it can be quite an aggressive and complex algorithm. But this then allows us to go right to the switching frequencies themselves and try and optimize the efficiency at that level. And this is important because whereas with a power grid using AC, all of the AC things are sinusoidal. With a digital inverter, they're not sinusoidal at all. So we can see that with this voltage signal, which is pulse width modulated. It's not sinusoidal. There can be more than 3 phases, so it could be multi-phase. And biggest of all, it's completely dynamic. It's not steady state. It's changing all the time, depending on where your foot is on the accelerator and how much power you're asking. So again, these are the key things. We can't just treat them as smooth sine waves like the power network. We have to take account that this is from a digital inverter. So using the ENCODE software where I come in, we can start to look at some quite powerful analysis techniques for that. So as I say, the journey starts with we've got to collect data. And the key thing here is it needs to be very high speed. So the eDrive system is very high speed, and it can collect data from electrical systems, and it can also do the torque data and things like that too, so mechanical. Each of the sensors needs to be very accurate, and it's going to cover a wide range of operating conditions too. So we need to collect all of those electromechanical systems. We need to consider them in a transient behaviour to look at that worldwide light harmonised vehicle programme, and also the system can pass information back to control systems as well through the test. And then of course what we can do is then analyse those data to produce those contour plots of efficiency. And our job is to maximise and broaden the range of those optimal areas to get the most efficient vehicle and configuration setup. And we usually do that through that digital inverter and the motor and the control system of that. Now, a lot of these are quite easy. To get that efficiency map, we need to calculate power. And DC, that's easy. Power is just voltage times current. Mechanical power, we know, is just torque times speed. And even kinetic energy and power, we can work out from GPS, as I'll show in a bit. The actual bit that's really demanding, though, is the AC. Now, if we were on a mains grid, then we'd use a power meter to measure the AC. And usually the electrical engineers will talk about this in terms of its active and reactive power. So active power is that's useful and it's used by the resistive load. It's that creates the heat in our heating systems, drives our factories and our lighting and things like that. That's the active power. It's doing real work. But there's also this concept that they call reactive power. So this is useless power really. And what it does, it comes from the fact that the voltage and the current are not actually in phase with each other. And what that lack of phase does is it introduces this sort of negative power when it's fed back to the grid. So it's not actively used, but it's polluting the grid. And so our electronics engineers, they want to measure that because they want to charge for that. And the apparent power is actually the total power provided by all of these. So on a normal power grid, we're used to these things, active and reactive and apparent. And my colleague actually, I think, explained that better than I just have. He says, if you imagine that this is a cup of your favourite coffee, a cappuccino, Then the apparent power is how much you think you're getting of the good stuff, the caffeine in your cup. However, the actual amount that you're going to get is the active power, and the other bit on the top is merely the froth and decoration, which is our reactive power. So I think that's a really quite neat analogy to active and reactive power. I like that one, so I'll put it in. Now, of course, we've got a digital inverter. So in this case, we've got multi-phasers. It's not sinusoidal at all, as we saw, and the amplitude and frequency vary all the time, because if we've got things like a synchronous motor, then the frequency will change depending on the speed of the motor and things like that. But we still need to talk about the apparent, active and reactive power. So again, the active power is that's the energy consumed to drive the vehicle, it's doing the good stuff. And the reactive power, this isn't consumed. But what it is it's creating heat losses, and they create all sorts of inefficiencies. So what's our goal? Well, our goal is we want an accurate measurement of that active power, because that's the parameter we want to maximise. But we also want a robust inference of the reactive power, because that's the power we want to minimise to get our efficiency up. Now you might be wondering, why have I chosen those two specific words? I have an accurate measurement of active power, and that's because active power is a physical quantity. You can measure it, and therefore that measurement needs to be accurate. But reactive power isn't real. It's a mathematical construct, and in this case we want to get a parameter which is robust. We don't want it to be sensitive to sample rates and many other things. It needs to be robust so that we can actually compare it and work to minimise it. So that's our goal. So if we have a look and see what the problem is, we can see here we've got our currents largely sinusoidal, but our voltage here is from a pulse width modulated inverter. And if we multiply instantaneously, we get this power signal. And of course, if we work out the area under this to look at the energy, we get some positive energy here. This is doing real work. We've also got some negative energy here. And this is the sort of thing that's leading to our reactive power. And again, we can look at this in the frequency domain. So these are PSDs. Here we can see our current and our voltage. We notice, look, with the current, there's our fundamental frequency. And we've got these tones out here, these switching harmonics from the digital inverter, but they're about 5 orders of magnitude less than the fundamental. And that's why this looks largely sinusoidal. But when we've got our voltage, look, we see that they're of comparable amplitude. And that's why we clearly see them in this case here. So we usually talk about this as being the fundamental frequency here. Then we end up with a spectral gap. And then we get our switching harmonics from our digital inverter here. And it's these switching harmonics which causes problems because it's not sinusoidal. So normally, when we're back at university, we learn the definitions of active power is just the average of the instantaneous voltage and current. And that's right, that never changes. That is the definition. However, we also learn that the definition of apparent power is simply the RMS of voltage times the RMS of current. And this is true for a sine wave, but it isn't true of non-sinusoidal. So actually, what we need to do with the non-sinusoidal is actually remember that, let me just flick back one in here. No, it's not going to flick back. So we need to actually remember that when we're seeing this, that those high frequency values, you can't just group them together as one sine wave, you've got to keep them separate. If you don't do that, what you find is that if we look at the green plot, this is reactive power. This reactive power looks really big, and it shouldn't be really big. It shouldn't be bigger than the active, because when we looked at that diagram, it looked like the reactive, that negative energy, was smaller. So what we need to do is the non-sinusoidal effects complicate this situation. That's what we need to deal with. And that's what we've done in glyph works with the new power analysis glyph, for example. So now with the new definition of broadband power, you can see we've now got that robust calculation of reactive power. And then we've got the accurate active power in here. So it shouldn't look like this, it should look like that. So we've got those capabilities we've been looking at for dealing with non-sinusoidal signals, power inverter signals. But also, we can actually go into much greater detail. So rather than smoothing this, we can actually use things like the Hilbert transform method, and we can zoom in on little artifacts in power, and we can actually look at what the switching frequency was doing at that time. And now we can go right into those high frequency switching modes and try and make more and more efficient systems to control it. So the key here is recognizing that this isn't a power line, that it's actually a digital inverter, and it means that we need to use some superior methods for our power calculation. But that's what we've been working on to help the customers. Now, another thing that they wanted was obviously they wanted to have better information of how vehicles are used in the field. So this started for me, well, many years ago, to be honest. A company I was working for then, they were looking for trying to work out how people were using their vehicles throughout the world, ready for hybrid vehicles and hybrid buses, city buses in particular. And the approach that we came up with was that, bearing in mind they needed 10,000 instrumenti, we used a mixture of CAN and GPS. So if we just use GPS logged at, say, 1 Hertz, let's have a think about what we can get out of that. So we know that the tractive power required is actually the tractive force times the speed. And we also know that the tractive force is a product, it's the sum of rolling resistance, air resistance, gradient resistance, and inertial resistance. So we can look at this, the rolling resistance. This is the aerodynamic resistance here. So when the velocity gets big, this becomes appreciable. We've also got gradients driving up and down hills, and the inertia accelerating it. And we actually found that we can be within 5 to 10% or 90 to 95% accurate on this. And the uncertainty actually amounts usually to the estimation of mass. If you've got one driver in here, or you've got 5 adults with their luggage, can make that big difference to the accuracy. But actually, it is a remarkably accurate assessment. One of my friends said. It just goes to show that Sir Isaac Newton was actually quite correct all those years ago. So if we combine those now, the GPS with the CAN, we can start to make all sorts of analyses. And none of these have to be, high frequency analyses. They can be quite lightweight and inexpensive data acquisition. In our case, it was mobile phones that we used to log them. And we can get all sorts of things. So for our city bus, for instance, it was important to know when most of the journeys started and ended. What was the idle time? What was the number of stop-starts? And how long did they spend at the bus stops? And how many times did that accelerate? Also, the breakdown of city, urban and highway roads. What was their traction power compared to their braking power, and how much energy was consumed rather than recovered? This all accounts to how you can store that and to work out the efficiency. We can also do other things too. So even things like cornering, acceleration and steering angle can be got from those GPS. And so by building these as histograms, it helps us to work out what is our target customer doing with the vehicle. So when we're looking at this, what are we looking for? So performance is all about getting a better real world range and a better energy density into our battery. And that means high speed data acquisition and logging and very accurate and efficient calculations. And they've got to then be able to replicate that real world conditions, so that worldwide light harmonized vehicle program. When we're looking at accuracy and thermal performance when it comes to that, we're interested in looking at the energy transfer from one stage to the other. And the key thing for us was to look at those AC requirements. So they're non-sinusoidal, it's frequency modulated, transient and multi-phase. And this leads to harmonic distortions, torque ripples, structural vibrations that can go into your battery, and efficiency losses too. So understanding those was a key to be able to improve the efficiency. But as I say, we're also after the better understanding of real world conditions. So just by trying to use existing data, so the onboard data on the vehicle, in addition to GPS, that meant that we could start to do statistical target customer analysis. And this also means that we can compare different usage of customers throughout the world, and we can also map those in time as well to look at changing trends. Because one thing I've found after driving one of these electric machines myself is it's quite exciting to drive. You tend to drive it a tad differently to you drive your diesel engine, and I think over time, I think most people take the benefit of that performance too. So that's a quick run through the performance. Let's finish off with the reliability aspects too. So in this case, we start really with FMEA at the bottom of this list. So FMEA is ideal where we've got new types of failure mode. So these are novel things, just like batteries are to us today. And this is a non-mathematical approach. It seems a bit simple actually, but it's hugely powerful. And this enables us to reduce our risk, especially with maintenance, with warranty items. Helps us to build that brand image for reliability, but also it helps build corporate knowledge and retain corporate knowledge. In addition to that, we don't want to forget maths. So we're looking at how do you do that battery life analysis, that state of health, and keep that using just the tools that we have available today. And then how do we do that tomorrow? How do we start to understand and model and reduce degradation? What should we be focused on? And I won't have time, unfortunately, to mention this, but there's also then the digital twin. So this is taking it to the actual vehicle platform itself and looking at how each vehicle is used and being able to map the state of health and the remaining useful life of those battery systems too. So first of all, what is reliability? Well, simply it's to ensure that our products perform their intended function, they perform them for the right period of time, in the right environment, and that they don't fail. So do what they're supposed to for as long as they're supposed to do it in the environment they've been designed to, and they don't fail. And there are many tools in reliability engineering. And we're just going to scratch the surface of a few, just looking at how we've applied them to batteries technology. So first of all, when we think about a battery, we have to first of all think of the different failure modes. So if you read any paper, the first one that comes out is thermal runaway. So this can be through internal short circuits or external short circuits or mechanical abuse, and that can lead to this catastrophic case of thermal runaway. Of course, the one that probably, from a durability and reliability purpose, excites us most is capacity loss. So this is the aging of a battery. And this can be aged mainly through charge-discharge cycles, so depth of discharge and the number of cycles, but also the calendar aging, so the aging effect of the electrochemistry as well. So both of those are critical. Of course, we've seen mechanical failures are really big. A lot of the latest research is showing that battery fatigue itself is equally comparable and probably more severe than electrochemical degradation right now. So that battery failure from fatigue is really important. But also the vehicle structural fatigue and using the battery as a part of the chassis is important too. And then when we look at the auxiliary systems on the battery, again, cooling it, controlling it, the battery management systems, these are important because if something goes wrong here, it can cause the battery to be operating in a non-optimal state, and that can create permanent damage and reduce our life expectancy. So how do we use FMEA, failure modes and effects analysis, to help improve batteries? So first of all, FMEA is simply a structured and methodical approach to identifying, mitigating risk and improving and reducing our warranty exposure. So it's a structured and methodical approach. So what we actually do is we identify potential failure modes for each item, we assess the risk, we rank them, and then we decide on corrective actions. And it's all done qualitatively. So when we're thinking about this, and it's all qualitative thought, we need a team of people because there's much more knowledge in a team than there is in an individual. So I think the first thing that I realised was don't think that reliability requires just the reliability engineer. The reliability engineer may be the chairperson of this group, but you actually need all the disciplines coming together. the designers need to come in and inform people about the problems that they've had and the challenges in the design. The test, what challenges did they have when they were testing it? What did they see was a problem? And the maintenance, what challenges are we actually seeing in the field? And then we've got the subject matter experts as well, all contributing to this. And the FMEA is a way of capturing knowledge, corporate knowledge, so it's reusable in the future. So how do we do that? Well, we start off really simply. We take down in our structure our battery and we break it down into its constitutive components. So our battery may consist of a number of modules. Each module has a number of cells. Each cell has a welded end cap. It's got an outer metal tube. There's a damper in it for vibration, of course. There's the cell itself, and there's a battery monitoring system in there too. There may be other things like the buzz bar assembly that we bring them into modules and things like that. So the first thing is to just break it down into items. And then for each item, we can go through a simple set of questions, and this is called the risk discovery. Now, they can be binary questions like yes, no, or they can be risk, low, medium, and high. And they're very generic. Things like, will the design involve new technology? So immediately we've got a red flag here. Is there a history of problems for a similar design? So this can cause another red flag. And simply we count the number of red flags each. And this helps us to our first stage of trying to work out where we should put our concentration first, where to prioritise things. So now we've done that, we can start to do the FMEA proper. So in this case, we take all of those items and we look at all the functions they're supposed to do. So our cell, for example, is probably supposed to provide a voltage of 1.2 volts for 85 amp hours, for example. We then look at what are the failure modes? So what is it that will prevent that cell achieving that? So one may be thermal runaway, for example. We then list the potential effects of that failure. So for thermal runaway, we could lose primary function of the cell, okay? But we can also, that may propagate beyond that individual cell, creating catastrophic failure of the entire pack and potential damage to the surroundings. So we can give this a severity index. So this is a value from 1 to 9 usually. In this case, I'd say fire was probably a value of 9. We can then go and look at all the potential causes of that. So it may be short circuit due to overcharge or discharging. And what's the percentage occurrence of that? That may be a factor of 3. So again, we can look at these. And now you've probably already realised what we're getting is a decision tree, a maintenance tree, if you like. So we can now look at potential causes and track back to root cause analysis too. So it's still very useful even at this stage. The next thing that we do though is we then look, what is it that we have to control that item now? So it might be that we've got current limiting fuses to stop the short circuits. And we can look at how effective are those. So this may be very effective, so it runs our risk down to 2. But for example, our electrolytic vaporization, our pressure detection may be not so good, so that's only 4. And what we do is we multiply these values together to get the risk priority number. And the higher ones are where there's the risk. And what we can then do is look at what recommended actions we have. And again, how do they impact that risk priority number? So failure modes and effects, it's a structured way of doing things, but its value is in knowledge capture and recycling. So even though it looks like Excel, whatever you do, use Excel for this because you lose its primary value, which is knowledge capture. So when we look at this, we've got the items and we've got the systems and we can reuse those. So when we build a new battery design, we can just import those in. So again, it's a very efficient way of storing knowledge and building it into new systems. So they can all be shared from a central database, but also they can be linked with other systems like the FRACAS, the failure reporting and corrective action system, and maintenance data. So as we get real in-service data, it comes to update our FMEA. So our FMEA becomes the repository of our knowledge on the reliability of this. And even as we start to do numerical reliability tests, those results feed up in and update our FMEA. So we can feed in with live data analysis and reliability centered maintenance and so on to build that knowledge base. So let's have a look now just at a little bit of that analysis, that numerical analysis, and see where we can go. So let's say what's the typical scenario for reliability of battery? Well, we sell our electric vehicles with a battery pack and with a guarantee. Now that guarantee may be something like 8 years or 100,000 miles, whichever comes first. But we know that the replacement of that is really expensive. So in those 8 years or 100,000 miles, how many failures do we expect to see within the warranty period? And how can we improve that and reduce our warranty exposure? So in order to do that, we need to look at the different failure modes. We need to recognise that there's generally two ways of addressing these. So if we have a look, for example, at capacity loss through cycle life or calendar fade, if you look in the papers, you'll find many different differential equations for different parts of this. It's quite daunting, to be honest. This is what we call a constitutive or physics model approach, and it's the way engineers like to work. However, we also acknowledge that there is a phenomenological model too, a statistics-based approach, and engineering is actually a compromise of using the best of both. If you think about it in terms of fatigue, for instance, we may use constitutive models like kinematic modelling to find out loads. We use FE to find out stresses. We're then going to use different things like maybe stress intensity factor solutions. But ultimately, we pair that with a statistics model, which is the SN curve, the EN curve, the DADN delta K curve. So we combine both the physics and the statistics together to make a workable engineering solution. And that's what we're also looking at with the loss calculations too, combining these two models together. And of course, there's also the ancillary systems too. So the cooling and the control system, we also need to build in as well. So they also have reliability models. So if we were to test batteries, then what we find is that we can create a life test. So if we're looking at the state of health, for instance, we see the battery coming along, and then periodically we start to drop off. And typically we take end of life as being something like 80% to 60% state of health, because after that it drops fairly quickly. Now we also know that no two batteries are going to last the same, very much like fatigue. There's statistical scatter, and we're going to get a distribution of failure lives. And for us in reliability, it's really important to understand that, because if we're going to set a warranty period, we need to know how many batteries are going to fail within the warranty period, and they're now on our dollar. So this is the key thing that we're looking about here. Now they will require us testing to failure, but thankfully there are ways that we can reduce the number of tests and also accelerate them. So for things like Weibull analysis, for example, rather than testing hundreds of batteries to failure, we're probably only going to be testing handfuls of batteries really. And we're going to then use that distribution to work out what is our statistical distribution and what's our confidence on that as well. So we can use a Weibull type approach for that and reduce the number of tests. But we can also accelerate the tests too. So found that, for example, the rate of health loss will increase dramatically with temperature, and it follows an Arrhenius model for that. We also know that depth of discharge affects it, and it's a power law model. This is very much like thermomechanical fatigue, to be honest. They're the same. And so what we can do is we can then combine those to create a hotter, deeper discharge to accelerate the test, so to get the 10 years worth of life or the 8 years worth of life in a much compressed period. Well, when it looks to how do we know what are the key parameters that affect it, we can do a Pareto analysis, and for this you'll see design of experiments used. So if we start off and we've got several parameters and we're not sure how influential they are, we can use design of experiments to create a series of tests to try and work out whereabouts is the problem here. So the Pareto chart can then help us to focus on the key things which are making the difference. That's how we obtain the depth of discharge and the effect of temperature on state of health. Now, when we're testing, we don't want to just test complete battery pack assemblies. That's really expensive and it probably won't achieve a good, reliable test. We actually want to test it using small economic tests and then build up that to make the battery pack. So we'll probably start by testing cells. And we know, for example, that cells are affected by calendar aging and cycle aging. Now, if we look at calendar aging, we know that the state of charge and temperature are the critical factors here. So we can use to accelerate the test and get the life curve for this failure mode. Now, when we look at cycle aging, then it's depth of discharge and temperature. So again, by using a high depth of discharge and a high temperature, we can accelerate those tests and again start to work out the probability distributions here. Now the modules as well, our key mode here is connector fatigue. Now this is very sensitive, as we know, to vibration levels and also the temperature cycling effects, the thermal effects of the battery giving you that constrained thermal expansion. So here we can use vibration testing and duty cycle compression to analyse that. And of course in the pack, which is largely structural fatigue, we've got stress and strain range. So here we can use a CAE-based fatigue prediction. So we've done simple tests. Some of them are simulation. They're not physical reliability tests. We now need to roll those all up into the full reliability of a battery pack. So we know at our cell model there are two failure modes in this case: cyclic capacity fade and calendar fade. And it doesn't matter which one kills your cell, each one will do the same sort of harm. It stops it working. So they're in series. Now we get to the module level, we've actually got a number of cells that are in parallel. So the death of one cell may not impact your reliable life of your whole pack. However, it's when you get several of them failing that you start to really see this degradation. So we've got this parallel here, but we've also got the added problem of connector fatigue as well. And now our modules are all combined together to make a pack. So now we've got each of the modules here, and we've also got our cooling and control system failures. And each of these have a probability and a life curve to them. So what we're now able to do is to combine in software each of these little tests into the big overall reliability of our battery pack. So say our target is to have no more than 5% failures at 8 years. We can see here that we're only achieving sort of, we've got a 20% failure rate at 8 years. So we're not going to meet it. But it also helps us to look down and see, so what's the primary cause of this? Maybe it's starting to be a mechanical problem with the system. That's our top target one. So this now enables us to go back into the model. Now we've seen that we need to do something, we can actually interrogate that statistical model and try and find out what's contributing most. And this again is quite good because it's not just the reliability, the sensitivity of each bit, but we can also weight it. So block 0, for instance, may be really important for reliability, but it may be almost impossible for us to do anything with it. So it's difficult to do very much here. And by this, we can weight these severities and therefore say, in this case, we need to attack block 4 and block 1, because then we'll be able to pull the reliability back in, because that's the biggest cause of risk. So in summary then, reliability is all about, it's not trying to predict one number. It's a bit like fatigue. We do not want to predict the life of which 50% of our batteries have failed. We're trying to understand the probability distribution so that we can understand the cost and the risk of failure. We also want to accelerate the test, so accelerate the temperature, the depth of discharge, to accelerate that and know how much that influences it. And we also want to combine the tests, so a small element test, combine them into the big pack. We don't want to be testing entire battery packs. We want to be testing smaller items that we can do more economically. So in the end then, what we're looking at here is FMEA is all about reducing our risk, building our brand image, but building our corporate knowledge. So FMEA is the repository of knowledge, and that's really good for novel failure modes in complex systems like a battery. it's reducing the risk of high impact failures. And FMEA can be done both for system, design, manufacturing and in the usage ranges as well. Then we want to reduce our warranty exposure today. So we may not understand all about the physics of batteries, but we have statistical tools that we can fall back on, and these are very reliable. So these are things like, what is the B10 life? So what's the life at which no more than 10% of our batteries are going to fail? We want to model the battery state of health by using statistics, and we want to therefore calculate remaining useful life of batteries. We also want to understand and reduce that degradation. So there's continual research going on right now about how batteries are working. And we want to integrate that too, but also use it in reliability analysis. Look at how the usage and charging patterns are influencing life. Look at the electrochemical degradation. Combine the tests with the real world data statistically to build those statistical models. And of course, I've not had time to talk about it, but there's the digital twin as well. This is all about reducing lifetime warranty costs, but not on effectively a vehicle platform, but each individual vehicle that we've got out. So by looking at the data from the CAN bus, for instance, can we build a model which is going to start to say, what's the state of health of these batteries and how much more severe are they being used, so that we can start to make changes before we start to see real maintenance problems developing. And also estimate things like remaining useful life, because that's going to be important when we come to resale values and things like that. So overall, this series of interviews with customers led us to a very full picture of what's important to customers, what's important today in building electric vehicles to be more efficient, to be more reliable and to be more durable as well. So I hope it's really helped you in that. And if you want to find more information, if you went to the HBM Prensia webpage here, you'll find these three areas with all of those three branches within more detail. And you'll also see that for each one, there's a webinar that you can log on to. And there's also a series of papers that you may be able to get to, not just from us, but from other organisations too. So I hope you've enjoyed the presentation, and thanks for joining us. And take care and have a good summer. Thanks, Sam.